Welcome back to another edition of The Explainer. I am so thrilled you're joining us today because, well, we've got a seriously fantastic scientific mystery to unravel. We are looking deep into the heart of hybrid rocket engines, specifically focusing on this completely terrifying phenomenon that engineers have literally battled for years. We're talking about violent, erratic shaking that can literally tear a rocket apart mid-flight. No joke. It's like this invisible sabotage happening deep inside the combustion chamber. So today we're going to play detective and figure out exactly how scientists are finally taming this beast.
So what exactly makes a rocket just shake itself apart? Think of the engine not just as a piece of machinery, but as an active crime scene. Something inside the airflow, something in the combustion process itself, is just going totally rogue. Engineers have had to meticulously trace the footprints of this invisible culprit, analyzing all the crazy thermodynamics and fluid mechanics just to solve the case. And honestly, what they discovered is nothing short of brilliant.
Okay, let's dive right into this. Here is our roadmap for the investigation. First, the shaking racket problem. 2, the physics of the wobble. 3, experiment 1, speed bumps. 4, experiment 2, the swirl. And finally, number 5, the perfect combination.
Section 1. The shaking rocket problem.
So, our culprit actually has a name. It's called low-frequency instability, or LFI for short. Now, LFI is essentially a series of really dangerous, totally erratic combustion pressure oscillations that happen at frequencies usually under 100 Hz. And guys, these aren't just minor little vibrations, right? They are powerful, nonlinear amplifications in pressure. They're triggered by the super complex interaction between the thermal lag, which is basically the solid fuel heating up, and the incredibly fast, turbulent fluid dynamics inside the chamber. If left unchecked, this low-frequency vibration acts like a literal sledgehammer from the inside out. It's fully capable of just completely destroying a rocket.
To really wrap our heads around this, we need to ground ourselves in the actual physical space of our crime scene. So take a look at this schematic on screen. This is the hybrid rocket motor testing apparatus used by the researchers. We've got 3 main areas here. There's the pre-chamber on the far left. That's where the oxidizer gas is injected. Then we have the long main chamber right in the middle, which is lined with the solid fuel. And finally, the post-chamber on the right before the exhaust nozzle. It is right in this tight, highly pressurized corridor that our erratic LFI completely takes over.
Moving on to Section 2, Physics of the Wobble. Okay, so inside that main combustion chamber, the airflow is just unbelievably turbulent. You get these small, swirling pockets of gas called vortices forming right near the burning fuel surface. And these vortices naturally generate these incredibly fast pressure waves, which the engineers label as P', and heat release waves known as Q'. As these little vortices travel down the chamber and eventually smash into the walls of the post-chamber, they break down. So the crucial point is this. When those pressure waves and the heat waves perfectly sync up with each other, it creates this phenomenon known as positive thermoacoustic coupling. Think of it as a totally destructive tango. They literally feed off each other, amplifying wildly and triggering that LFI sledgehammer effect we talked about.
You don't even have to just imagine it, because you can see the terrifying symptoms right here on this baseline chart. Take a close look at those erratic, jagged red spikes that totally dominate the middle and the end of the timeline. That right there, that is the LFI completely taking over the rocket. The pressure is just swinging wildly, jumping up and down with immense force. And this is exactly the chaotic behavior that engineers absolutely need to stop.
Which brings us to Section 3, Experiment 1, Speed Bumps.
So the big question is, how do you actually stop a microscopic, destructive tango? Well, researchers realized that if LFI relies on this perfectly smooth, uninterrupted boundary layer of airflow to let those waves sync up, then they just needed to disrupt that flow. Their genius solution? A chemical speed bump. See, the main rocket fuel is a type of plastic called PMMA. It burns fast, and it leaves a really smooth surface behind. But the researchers decided to insert a tiny ring of a completely different plastic, high-density polyethylene, or HDPE, smack in the middle of the main fuel. Because HDPE burns slightly slower than PMMA, as the rocket fires, the surrounding PMMA burns away much faster. This leaves that slower-burning HDPE ring jutting out, creating a literal physical bump right inside the chamber.
And this graphic brilliantly illustrates exactly what happens over time. If you look at these 3 cross-sections of the fuel, in the very first image you can clearly see that physical step. Our speed bump is standing tall and proud. This bump physically disrupts the airflow, it changes the size of the vortices, and it basically scrambles those pressure and heat waves so they absolutely cannot sync up. It delays the instability beautifully.
But if you look closely at the second and third images, you start to see the fatal flaw. Eventually, the intense heat inside the rocket just melts that speed bump completely flat, and the very second it disappears, the LFI comes rushing right back in.
So, to combat this melting issue, engineers ran Test 2, but this time they used 2 HDPE speed bumps. If you compare the totally chaotic baseline on the left with Test 2 on the right, it is night and day. The pressure on the right is incredibly smooth. By using 2 speed bumps, the researchers created something they call negative coupling. Essentially, the pressure waves and heat waves were forced completely out of sync with each other, meaning their peaks and valleys basically canceled each other out. The destructive tango was totally stopped in its tracks.
All right, Section 4. Experiment 2. The swirl.
Now, while Test 2 was a definite success, those physical speed bumps still have that one fatal flaw. They're literally made of fuel, which means eventually they will always melt. The team realized they needed a more permanent disruption. I mean, if a physical speed bump melts, why not just create a hydrodynamic speed bump out of the gas itself? Enter the swirl injector. Engineers went in and modified the front pre-chamber to inject the oxygen not just straight in, but at an angle. This adds a literal twist to the oxidizer flow, creating this incredible spiraling tornado effect right down the length of the rocket. This continuous swirling motion constantly disrupts the boundary layer near the fuel surface. It stops those bad synergies from forming, and the best part? It never melts away.
But, aerospace engineering is never ever that simple. This brilliant fix actually introduced a brand new problem. Yes, the swirl injection completely changes the flow dynamics, and yes, it absolutely stops the shaking. But that swirling tornado effect also causes the fuel to burn incredibly unevenly. It gets concentrated heavily right at the front of the rocket. So if you apply too much twist, you completely ruin the engine's fuel efficiency and drop the overall pressure. Sure, the rocket might be totally stable, but it's not going to fly very well. The engineers realized they needed to find the perfect, delicate balance.
Which leads us to Section 5, the perfect combination.
The researchers went back to the drawing board and ran multiple variations. They meticulously adjusted the angle of the swirl, they moved the position of the fuel inserts around, and finally, they hit the absolute jackpot in what they called Test 7, the Goldilocks zone. The precise recipe for success turned out to be a very modest 6-degree angle on the swirl injection paired with a single HDPE fuel insert placed exactly 310 millimeters down the chamber. This hyper-specific combination was the magic bullet they needed for total FIL suppression. Now, what's really interesting about this slide is the undeniable visual proof of their success. On the left, we have our chaotic, violently shaking baseline, but look over at Test 7 on the right. It is just beautifully stabilized. The pressure holds steady and firm, right where it should be. The combination of that slight swirl and the single, carefully placed physical speed bump permanently shifted the pressure and heat waves out of sync. That terrifying sledgehammer effect completely neutralized.
But wait, remember our swirl problem? Did this fix end up ruining the rocket's overall performance? Well, let's walk through this data table together to find out. Take a look at Test 3, which was an unstable run. The average pressure is sitting at 1,041 kilopascals. Now look down at our Goldilocks run, Test 7. The pressure is actually a little bit higher and healthier at 1,082 kilopascals. Plus, the oxygen-to-fuel ratio and the fuel regression rates, which are both absolutely vital metrics for fuel efficiency, are sitting in a perfectly reasonable range. It's way better balanced than Test 8, which relied entirely on a really high 9-degree swirl. So Test 7 proved once and for all that you can absolutely stabilize the rocket without compromising any of the engine's vital performance.
And that, my friends, brings us to our conclusion. Disrupting bad synergies is the true art of aerospace engineering. By taking a step back and literally forcing the microscopic waves of heat and pressure out of sync, these engineers saved the entire vehicle. It really makes you wonder, doesn't it? What other invisible chaotic forces in the world, whether that's in a machine, a complex system, or hey, even in our own daily lives, just need a tiny, carefully placed speed bump to be completely stabilized? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I will see you next time.